Okay. Okay, I'm going to pass around some old work that I have of yours. There should be, I believe, 2 or 3 things in here. There's the quiz that we took. I don't remember the date on this, but I think there's 3 quizzes in here. So just take yours out of there. The grades for 2 of those are online, but they're not written on the test or on the quiz. All right, so we are. How far away are we from our next exam?
1 week.
1 week. A week from today. Okay.
Any chance we could maybe get the set list for it?
The list what?
Can we get the set list for it? I guess the reason why I ask is because there's like a
set list of what?
just an alliteration to how many questions are there?
Oh, I'd have to have the test made to be able to tell you that.
Well, let me ask you a question.
Okay.
There was a rumor going around that the actual definite integrals will not be on there. Is that the case, or was that mistaken? Just wanted to clarify.
Right. That's a mistake. Not sure where that would have come from, but
I have no idea. I just wanted to make
okay.
clarification.
So let me see. Where are we here? 6-6. All right. So last class, we established a very nice result that was tied to the fundamental theorem of calculus. Basically what we said is this. We said that if we have some function f on some interval ab, that what we can do is we can find the area under it, right? Now, I'm going to put some stuff up here. It's going to be kind of visual, and it's important as we proceed through this class that you understand how the visual part of this connects to the notation that we use. So just trust me on this. It'll help later. The idea here was that we wanted to fill this thing with rectangles, right? And we wanted to let that number of rectangles go to infinity. So generally speaking, what we're doing is we're taking our function, we're creating this rectangle inside of it, and we're going to find the area of that, right, of that rectangle. And once we find the area, we're going to add up all those areas. And when we do that, it's going to wind up being an antiderivative, right? That's how we'll do it. But in terms of notation, if I look at that little rectangle by itself over here, the height of that rectangle is the function's value, right? So the height of that rectangle is the function's value at certain points within the interval, right? But generally it's just the height is the function. And then the width of the function was always the same, wasn't it? Like each rectangle had the same width. And that was how much x changed by as we moved through. Right? We did this when we did the Riemann sums. So we could call this, I don't know, like a change in x, right? Delta x for like change in x. That's how wide each one is. And so the area of this, the area would be f of x times delta x. Now, what we did was we let the number of these things go to infinity, the number of rectangles, which made this width become infinitesimally small, right? And when we start talking about infinitesimally small, this delta x changes. So I'm going to put here, when the number of rectangles goes to infinity, this formula changes to this, dx. dx is the notation we use for delta x when we let it become infinitesimally small. Right? So dx is an infinitesimal change as opposed to delta x. Does that make kind of sense? When we take the limit, this becomes a dx. And so this gives us the area of one rectangle, right? And do you remember in the Riemann sums, we use that notation to add things up, right? So what we do is we want to add these up, right? But we want to add up an infinite number of them. So we don't use this notation anymore when we want to add up an infinite number of things. We use this notation. Okay, so this integral sign actually comes from this idea of the Greek capital letter S. This is like an S that's been stretched out. It's just a long S, right? So that integral sign represents this sum if we let the number of rectangles go to infinity. Right? So from now on, I want you to be looking at an integral sign as a way of adding up an infinite number of things. All right? And then what are we adding up? All the areas, right? So the areas have this formula. And that's what we've seen from the very beginning, right? The integral of f of x dx. So we've been dealing with this the whole chapter 6, right? Trying to find antiderivatives. But we added one more kind of layer on this. We put these numbers here, a and b. And that was just notation to let us know that we are going from this endpoint to this endpoint, right? Okay, now what did we say? The main result from last class was that this, right? This area, which represents the area under that curve, is equal to what? What's the big result from last class?
B minus A, or A minus B, excuse me.
It's some b, something. The function evaluated at b minus the function evaluated. What function evaluated at b?
Capital F of x.
Capital F of x, which is the antiderivative. So we find the antiderivative of this. We evaluate it at that endpoint. We subtract from that the antiderivative evaluated at the other endpoint, and that will give us our area. And that was the main result from last class, right? Okay. But again, I can't stress this enough. When we see this notation, what we should be thinking is, all right, we've got these rectangles, right? They have a height of f of x, a width of d of x. And what we're going to do is we're going to imagine starting that rectangle out here. It's like infinitesimally thin. And then we're going to slide our way across and add up all these areas across. So the adding them up is this. This is the area, and the A and B tell us where we're going to be sliding from which side to which side. Yes? Okay, that's going to help, trust me, later when we start doing other crazy things with this, all right? Okay. So what we still need to do is maybe a few more examples, and then we're going to get into the next section, which is 6.6. So here's one we did not do last time. All right, so this is now a definite integral, right? Because we have these numbers which we call the limits of integration. So the first step for you is to figure out what the antiderivative of sine of x is, right? So what we did was we said, okay, write down the antiderivative. What is the antiderivative of sine of x? Negative cosine of x. We write it down, and then we put this bar here. We put 0 and we put 2 pi. This was just notation that we used last class to help us be able to write the antiderivative down before we actually plug anything in, right? So now let's plug in. And I like to do 2 sets of parentheses. And what gets plugged in first? 2 pi always goes in first. So what is well, I'll just write it down first. Negative cosine 2 pi, and then we're going to plug in negative cosine of 0, right? So what is cosine of 2 pi? 1? So this will be 1, right? And then negative. So this is negative 1 minus, okay, what's cosine of 0? 1, so minus 1, so we have minus minus 1. Is that right? Right? So what do we get? 0.
Does that mean it stopped at the y-axis?
Well, we know what that graph looks like, don't we? Okay, so that's why it gave us this example, because we actually know what sine looks like. We know what it looks like between 0 and 2 pi. If we draw it, it's just one period, isn't it? And what we've discovered is that the area underneath this, when we use this formula, the area is actually 0, which doesn't make sense because it does have area. Obviously, it's counting the area that's above the x-axis as a positive area, and it's counting the area that's below the x-axis as a negative area, right? And so they're canceling each other out because of the symmetry we have between those two arcs of the sine function. So it's kind of weird that we have a negative area, right? But just think about your rectangle. When your rectangle's over here, remember the integral means we're going to slide a rectangle across, right? So when your rectangle's over here, it's going to be the height times the width, right? And the height here is positive because we're up, right? So when you take a positive number times the width is always going to be positive. It's going to be a positive. It's going to count it as a positive area. But when we get over here, right, when we look at the height of the function, it's below the x-axis, so it counts it as a negative number. So negative times the width, positive, you get a negative. So they're going to offset each other. So that is one kind of drawback to this definite integral, is that it does not distinguish like when our graph goes below or above the axis. We have to figure that out. So if we wanted, this gives us like a net result. The net result is 0. But what would be the total area treated almost like an absolute value? Could we figure out what this area is plus that area? Like as true areas? How could we do that? How could we change the problem to make it, to get an answer other than 0? Because I am really interested. I'm sure you've sat there and thought to yourself, like, what is the area of that arc of sine? Yes, that's something yeah, of course, right? But it would be kind of interesting to know what that area is, because this is a very weird shape. It's not a circle, right? It's just an arc of the sine function. So I wonder what that area is. So what could I do a little different to figure out what that area is? Yeah, just go from, instead of 0 to 2 pi, why don't we go from 0 to pi and stop there, right? That should give us that area. So if we just change the problem, we just go from 0 to pi, sine x dx. We still have the same antiderivative. It's our evaluation points that are different, right? So now we go negative cosine of pi, and here we go negative cosine of 0. So the only change here is this one right here. What does this become? This is going to be cosine of pi, right, which is negative 1, but then negative, so positive 1. So this is 1, and then this one we already know turned out to be what? Minus minus 1? So what's the area? 2. Does that seem weird? I mean, that's always seemed weird to me, that the area under one arc of the sine function is a nice number. It's 2. Seems strange to me that it would turn out to be that way, but it is. I mean, that's what it is, okay? So if this is 2, this area is being counted as negative 2. But you wouldn't have known that from just having an answer of 0, right? You don't know if maybe this was like pi and that's negative pi, but you can't tell unless you stop it somewhere, all right? Which means you need to know where this is, right? You need to know that that was pi. So if you were given like some arbitrary function, like a polynomial function, and you wanted to figure out this area right there, you would need to be able to find these two x-intercepts, wouldn't you? And if you could find the x-intercepts, those x-intercepts would represent your limits of integration, and then you could integrate there and find the area of just that little piece, okay? But if you integrate along the entire way, or if you go further out or something, and stop here, it's going to count some positive, some negative, some positive, some negative. So you're not truly getting an accurate measurement. Does that make sense? Okay. Now, what about something like this? Trying to think of where I want to go with this first. Do you all feel like you have like a general idea, feeling for what the definite integral is? Area, the only difference is now we have these 2 points where we're going to evaluate, and that's pretty much it, right? We have all these techniques of integration, so we should be able to handle integrals, right? Definite integrals. As long as we find the antiderivative, plug into endpoints, that's the only difference. Okay, so let me put up here a problem and see if we can maybe wrap our heads around what we need to do. So how about this? I'm going to look at this function of x equals 1 over x squared, all right? And to help us graph this, or to help us do this problem, I'm going to just draw the graph of this real quick. It goes like this. And on this side it goes like this. All right? So that's the graph of that function. Here's what I'd like to figure out. I want us to find the area on the interval 1. So I'm going to start here at 1. Okay, and I want us to find the area. Let's see, where do I want to stop? Where do I want to stop? 10? We could do 10, right? And then you just find the antiderivative and plug in 10 and you can figure it out. Let's not stop at 10 then. Let's stop somewhere else. Let's see. How about we just don't stop? Yeah, why don't we go to infinity? Why don't we go to infinity? Does this even make sense? I mean, you have area, right? You have area, but as you get further out, this thing starts to diminish and get closer to 0. Does it ever get there? No. Okay, so we do have area, like we're always going to have some area being contributed, right? So any ideas on what our answer should be then? Like what would the total area be? Like you start here, we start getting area, area, area. As we keep going out, it's getting smaller, but we're still getting area, right? And we never stop. So do you think it's going to like overfill and just become infinite? Maybe.
In our case, it'd probably be negative infinity, actually. That's going to be on the second part, the second half.
On this, no, these are all positive. They're all above the x-axis, so it'll all be counted as positive, right? I think it's completely logical right now to think that the answer should be infinite. I think that's completely logical because you can make the argument that, if you stop right here, let's say we stop right there, that right there, right, is going to be a positive number. Agreed? Okay. Now, if I go out and I stop somewhere else, right there, like from here to here, that's going to be a positive number, right? And if I just keep going and stopping and going and stopping, each one of those is going to be some positive number. And if I just keep doing that forever, I'm just adding a positive number on top of a positive. And so, the cup runneth over at some point, yes? Like you can't say it's finite because, so I think it's a good argument, but it's not going to happen. So let's see what happens, all right? So let's follow the procedure. The setup of this would be integral 1 over x squared dx. Now what are my limits of integration? 1 and up here infinity. So now this is the first time we've seen this, and these are called improper integrals. In fact, what we're looking at here are referred to as, these are called type 1, going off what the book says, type 1, and type 1 are infinite intervals. In other words, the interval we're looking at is infinite, isn't it? So the interval of integration, what we're integrating over, is an infinite thing. And so the type 1s that we're going to deal with right now are these type, where this thing is infinite. Okay, well, let's follow the same procedure, right? But infinity is not a number, right? Infinity, we can't, you know how when we do the evaluation, we plug in the B, we plug in the A? You can't plug infinity in. Like infinity doesn't work that way, right? What we can do is look at infinity as like an idea, like a limit, right? It's like we can let something become very big, right? So what we'll do anytime we have this is we will first convert the problem over to this, limit. Now I can use any letter I want here. The book uses t. The limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. So all we said is this. We want to figure out what the area would be if we went from 1 and then stopped at t. We should get an answer for that, shouldn't we? And that answer should have t in it, because t is a variable, so we don't ever get like a numerical result. So this right here should be an expression we get with t in it, and then what we're going to do with that expression is then let t go to infinity, and we're going to see what happens. So now, I'll continue over here. I want the limit as t goes to infinity. Now I go ahead and go through the work here. What's the antiderivative of this? Is it negative 1 over x? Should be negative 1 over x. So yeah, because you're rewriting this as x to the negative 2 and then doing the antiderivative, right? So add 1, blah, 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 all that stuff. So that's the antiderivative, yes? But then we need to do the evaluation bar, and we're going to go and evaluate from 1 to t. Okay, so this step right here, the limit's just sitting here waiting, right? We haven't done the limit yet. This part here is the next step of this piece, right? Take the antiderivative, evaluate the two endpoints. So now let's go ahead and evaluate at the two endpoints. And I'm going to do it like this. So what happens when I plug t in for x? What do I get? I get negative 1 over t, right? So t goes in right here, so I just get negative 1 over t. And then I say minus, now I plug in 1 for x, and I get negative 1 over 1, which is just negative 1. Right? Now at this point, we've done the antiderivative, we've evaluated the two endpoints, right? We've used the fundamental theorem of calculus. And now this is the expression right here. This is the expression that would give us the area, right? If you told me what t was. So if t was 10, right? We said 10 earlier. If you plug in 10 right here, do this arithmetic, that's going to be the area. If you give me 100, then that's going to be the area. Understand? But I don't want t to be 10 or 100. I want t to become infinite. So I take the limit of this. And when we look at this and let t go to infinity, what happens? What happens to this? That goes to 0, doesn't it? This becomes infinitesimally small. It goes basically vanishes away to nothing, right? And then this over here nothing happens to it, right? So you have minus minus 1, so that's just 1. So once you apply the limit, your answer is 1. So what this means is this. We're looking at this graph. And we want to know the area forever this way. The answer is 1. Now, we mean that if I were to go and stop at 10, I know that my answer wouldn't be 1, but it would be close to 1. If I stopped at 100, it would be even closer to 1. If I stopped at 1,000, it would be even closer to 1. Right? So maybe I stop at 1,000, maybe it's like 0.99999, right? I stop at 1,000,000, maybe it's like 0.99999 with like 39s. If I stop at 1,000,000,000, it's going to be like maybe 0.9 with like 1,000 nines. I can't stop at infinity, but what I can tell you is that the further and further I go out, the closer and closer and closer I get to 1. That's the way limits worked, right? As something approached something, something else approached something else. So we are saying that the answer is 1, but we're approaching it. We actually never get to it. We never get to 1, because you would eventually have to stop if you ever want to know the answer, right? Okay. That makes sense? All right, so let's try the same problem, but I'm going to make a very slight change. Let's do 1 over x. Okay? So how does that change things? Well, we still do this, integral from 1 to infinity, right, of 1 over x dx, right?
It's going to be the natural log?
Yes, so we do that, right? That's this. And now what we do is we replace the infinity with a t and we put a limit out front. And now we go ahead and find the antiderivative. This time it's natural log x, right? Now it's supposed to actually be natural log of the absolute value of x, right? Yes? But the thing is we are going from 1 to infinity, aren't we? So x is always going to be positive. So we don't need the absolute value, but I'll put it there just to have it. Okay, I realize you're having to write this down. I'm just like erasing. So y'all got that? This, and then here, and now, how does that change those two pieces in here? So we do, t goes into here, right? So we get natural log of the absolute value of t, and then minus natural log of 1, right? Now the natural log of 1 is 0. But what about natural log of t? What happens when you let t go to infinity here? As t goes to infinity, that becomes big. You're basically saying, what does the natural log function do as you draw it out to the right forever? So you have to remember what natural log looks like. So natural log function looks like this, right? So if we want to know what natural log of infinity is doing, we look at the natural log function, we start going out this way, and we look at what happens to it. So what's happening to it? It actually grows, okay? Now, it doesn't grow very fast, but it does grow. So as you go out to infinity, what does natural log do? Heads up to infinity also. So that means this heads where? To infinity. And infinity minus 0 is still infinity. So what's happening here? Yeah, so it's blowing up, right? This thing, the area is accumulating too fast, and it is overfilling the cup, so to speak. So what we say here, we have a terminology for this, and we use this back in Cal 1. We would say that this integral diverges. Okay, so this right here, because we got infinity, we will say it diverges. Diverges just means it's not going to something in particular, all right? It's not going to an exact place. Did y'all catch that? If it goes to infinity, it means it's not headed to a number, right? Because infinity just means taken off, right? What do y'all think? Understand? Okay. Let's do another one. What do you think it was about this one versus the other one that made this one, the total area under that from 1 to infinity, that area was converging to 1, but this one right here was diverging? What is it about those two, the difference that you think makes it happen?
Maybe because the squared makes it go quicker?
Yeah, the square definitely makes the denominator grow faster, right? So as I'm graphing this one, what's happening, like if this one is the 1 over x, right? If that's this one, then 1 over x squared is going to, they're still going to start there, because at 1 you get 1 as an answer. But because you're dividing by x squared, it's actually going to dive down faster, so it kind of decays away to 0 quicker, and that's what forces the answer to have a number instead. The 1 over x, even though it does die down, just doesn't die down fast enough. All right? All right, let's do this one. Any questions or no?
The only type is there?
There's going to be 2 types of improper integrals. Okay, so let's do this one. I want us to look at the function sine x, and let's do it on the interval 0 to infinity. So just think about this first. Does anyone have like a conjecture here as to what you think the answer is going to be? Do you think that it's going to converge to some answer? Or do you think it's going to diverge, which means that the area is not headed towards a fixed number? What do y'all think? And what would be your... I think it's going to...
Periodic, that might head towards 0.
Okay, so one idea here is that if we look at the sine function, right, it's just going to keep doing this, right? So you're thinking, okay, like as you go out, these are just going to continue to like offset each other, right? Okay, so you're saying 0 maybe? Any other ideas, or we all think that it's 0, or anyone think it's going to diverge? So here's the problem. Here's the problem with the idea that this is going to converge to 0. Here's what's wrong with the idea. Let's say I go out, and you know, like I'm going out, I'm walking along, and then someone tells me to stop. Do you think that the total area accumulated is going to be 0 at that random instant? Probably not, right? So like maybe I come out here and they tell me stop right there, okay? Then I'm going to have that area, and then this, and then that, and this. So everything back here is going to cancel, right? But I'm going to have some little area there, right? All right, so then I keep going and I go to a different place, stop. Maybe I'm at 0 there. Maybe they will all cancel out. But if I'm going out to infinity, as I'm accumulating these areas, what's happening is, I mean, think about it right now. Think about the answer. If I start going out to infinity, right now the area is 0. I go out, what's the area from here to here? Well, we found it's 2, right? But it's positive, yes? And then right now from here to here, what would our answer be, positive or negative? It's still positive because we have this being offset by this, right? So we have 0. Positive, 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 right? And then 0, and then positive, 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 0. Positive, positive. So what's happening is as you move across, if you're just looking at the total area, it's like it's going up and then back down, and then up and then back down, and then up and back down. The area is doing that. And so when we're saying, is this thing converging, we're asking, is the area headed to one thing? And it's not. It keeps oscillating. Does that make sense? But let's see how the math shows that to us. So the integral is going to go integral 0 to infinity sine x dx. All right. This is going to convert over to limit t goes to infinity of integral 0 to t sine x dx. Okay, so anytime we see an improper integral where we have an infinite interval, we want to replace the limit of integration, and we want to do a limit. Okay, this now becomes limit. T goes to infinity, and then the antiderivative sign we already know is negative cosine, evaluated 0 to t. And that means we have the limit as t goes to infinity. I like to do my parentheses like this. All right, so first we plug in t, so negative cosine t. And then we plug in 0, negative cosine 0. So what does this become? That's going to be 1, negative 1, right? And then another negative. So all of that together will be plus 1 over here, right? All that's plus 1. But what about this? As t goes to infinity, right? As t goes to infinity, what does cosine t do? So think about the cosine function as you go out to infinity, right? It just keeps going up and down. It's not headed to anything, right? So this right here, this limit, if we just isolate ourselves into this little world right here, back in Cal 1, we would say that this limit does not exist. Do y'all remember seeing this in Cal 1? This limit doesn't exist. Cosine oscillates, it's not headed to anything. If the limit doesn't exist, right, then this integral doesn't have a number it's headed towards. Okay, so we would say in this case, it diverges. This integral diverges. So diverges The problem with the word diverges is most students think the word diverges for an integral means that it becomes infinite. That is not what we're saying. Divergence means not convergence. Does that make sense? Like if it does anything other than converging, it's diverging. In order for it to converge, this would have had to have gone to a number, and then we get a final answer, 4, or whatever it is. If it does anything other than that, it goes to infinity, or the limit doesn't exist, anything weird like that, diverges. Okay? All right. Let's do another one. I have notes for this in Canvas. I have notes for this section, but I'm just having one of those days where I just want to wing it. I just want to wing it today. Shit, did I hit record? Yeah, okay. I've spent the better part of the last 48 hours at the vet with my dog, and it's been, like dogs always seem to have issues like when the vet's not open, so I've been at the emergency vet, and it's, I was there from 9 to like 2 a.m. last night, like 9 p.m. to 2 a.m. And most of that was just waiting. It sucked. So I'm tired. That's why I'm winging it. All right, got that function? I want to look at that function because we actually haven't really spent any time looking at this thing, have we? I'll draw it for you real quick. What's the value of that function at 0? 1? Okay, so tell me what happens. Let's say if I plug in 1, what if I plug in 1 to this? What's the value? A half. What if I plug in 2? It's going to be a fifth, right? Plug in 3, it's going to be a tenth. So it's like as we go out that way, it's starting to die down, yes? What if we go out the other direction? Same thing, exactly the same thing because it's squared. So it's like it's symmetric, right? Oh, it's symmetric to the y-axis. So if you graph this, it actually looks like this. Okay, that's what that would look like. So I'm interested to find the area, guess where? The whole way. The whole way. On the entire number line, what's the area? Okay. Well, we have a little bit of an issue here because our limits of integration, we have a lower limit and an upper limit, right? We want the upper limit to go where? The upper limit, we need that to go to where? Infinity, and we need the lower limit to go to negative infinity, yes? So we actually need to do 2 limits. We need to do the limit for the top part and the limit for the bottom. So here's how we're going to do this. We're going to first write it down. We're trying to go from here to here of this, right? That's what we're trying to do. So what we'll do first is we will go from negative infinity to 0. I wrote it the wrong way. It's still right, but. And then we're going to go from 0 to infinity. Now, do you agree this should still give us the same answer? I mean, basically we have, like, this integral right here represents the area over here, right? And then this integral right here represents the area over here, and we're just going to add them up, right? Does that make sense that we could do that? Okay. That looks like plus or minus. Sorry, I'm going to take that out of there. Okay, so we're just going to do these 2 separate integrals and add them. So for this first integral, I cannot put infinity in my integral. So what I'm going to do is a limit, right? So I'm going to do the limit as, I'll use t again. T goes where? Where's t headed here? negative infinity, right? And then we're going to do integral t to 0. Oh, by the way, I should point out that, you know, I went to 0, right? I went from negative infinity to 0 and then 0 to infinity. I should point out I could have stopped anywhere. So like I could have gone from negative infinity to 10 and then from 10 to infinity. It doesn't matter where I stop in there as long as I stop somewhere and then pick up and continue. Does that make sense that would work? Just 0 just makes sense because it's right in the middle. Yes?
That's supposed to be 1 plus x squared.
I wrote it backwards on accident, but they mean the same thing, right? Okay, and then in here, 1 over 1 plus x squared dx, right? That's the blue integral, right? That's the blue one. And then I have plus, now another limit, right? Another limit. And this time, I could use t again. I could. But I'm just going to use a different letter, just because I don't want us to be mixing things up. So I'm going to use s maybe. S goes to infinity. You could use anything. You could use anything you want except for x or t. Just, you know, any other letter. If that s looks too much like a 5, use r or something. Okay, integral is going to be from where to where? 0 to s this time. God, I really regret using s right now. It looks too much like a 5. I mean, I know it's an s, but I mean, yeah. Yeah, and we're leaving it. Leave it or no? Change it?
Or something, or like a W or something.
I'll put r. I'm going to put r. Certain variables are used for certain things. R. I could, yeah, I mean, omega, not really. Most of the time when I see limits, I see like t, s, r, x, y, z are reserved for these variables. You know, c is reserved for like constants. So there's just certain things that are kind of protocol without being like, it's like understood but not a rule. All right, we good? So now we got to do these two. Now the antiderivatives. I should call on somebody. I should like pull a stick and ask what the antiderivative 1 over 1 plus x squared is, and if they get it wrong, go take them to the attendance office and drop them from the class. No, there was a professor I had that did that.
Wow.
Yeah, but it was because one of the students in the class, I'll never forget it, it was a number theory class, which is about a junior level math class, and one of the students in the class asked, why do we need to know this? So everyone in there is a math major pretty much, or like computer science or something like that. And at that point, you stop asking why you're learning this, because you're learning it because you've chosen to learn it, you know? So he asked that, and the professor stopped the class and took him outside. We didn't know what happened. And about 30 minutes later, the professor came back, and we're like, what the hell? And the other guy never came back, and we found out he had taken him and dropped him from the class. Okay, yeah, it's pretty brutal. All right, so antiderivative. What is the I'm not going to do that. I'm not going to. That would just be fun, right? Just to see like what came out on the news and stuff. Professor drops student for getting answer wrong in class. Okay, antiderivative. What is the antiderivative of this? Arctan, right? So arctan x. So arctan x. And the evaluation bar is going to go from t to 0, right? Like that. And then we have this one, right? So plus the limit is r goes to infinity of arctangent of x again evaluated 0 to r. Are we good? Y'all understand where all this is coming from? Sure? Okay, now for each of those, I'm going to do my little parentheses for each one and make sure that I'm writing the limit out front. So we have two sets of parentheses. I'm just going to set everything up first. All right. So in here, we're going to do, let's see, what's going in here? arctan of 0, right? And here, arctan of t. And then in this one, arctan of r. And then in this one, arctan of 0. Okay, again, everyone understand where all that came from? Any questions? You sure? All right. Two of these things are pretty easy, but I know people are going to have trouble with the others. So when we're talking about the arctangent function, it's the inverse of tangent, right? So the way that I've always thought about it is I don't have the graph of arctangent in my mind. I have the graph of tangent in my mind. So I think about tangent. The tangent function does this, right? Now this you have to know, right? You just have to know what tangent looks like. This is tangent of x. That's this graph, right? So when you're saying what is arctangent of 0, what you're saying is look at the tangent function. Where's the y-coordinate 0? So where on this graph is the y-coordinate 0? At x is 0, right? At x is 0, the y is 0. So this is 0, isn't it? This is 0. And this is 0. Right? Now, we need to know the arctangent of t, but t is headed where? It's headed to negative infinity. So this is really saying arctangent of something that's becoming infinitely negative, right? So you go to your graph of tangent and you ask yourself, where is my y-coordinate becoming infinitely negative? Right there, which happens at this asymptote, right? This asymptote is negative pi over 2, right? So even though I can't plug negative pi over 2 into this, this is a limit, right? So it's asking what we're approaching. So in order to make the arctangent function become no, I said that wrong. In order to figure out what arctangent of something that's negatively, becoming infinitely big negative, right? I need to know what angle that corresponds to, and it corresponds to negative pi over 2. So this result right here is negative pi over 2 in the limit, when you take the limit. Okay, with that same argument, what's the answer to this part? Positive pi over 2. Because now you're plugging in infinity, right? So you're saying, where's the arctangent function becoming infinite? That means where's the y-coordinate on tangent becoming infinite? It happens right here at this asymptote, which is pi over 2. Yay or nay? Yay. Okay, so let's see. We can put this all together. We've done the limit now, right? We've done the limit. So no more limit. This is 0. This is minus pi over 2. So that's plus pi over 2. And then plus, over here we have pi over 2 minus 0, so that's just pi over 2. And that means your answer is pi. So the area underneath this function on the entire number line is pi. So if anyone ever asks you what pi is, right? Say, hey, what's pi? You could say, you could give them the good old definition of if you take a circle, right? You take the circumference and divide it by the diameter, and that's the that's like the most generic definition of what pi is. Draw a circle, its circumference divided by its diameter is pi. That's a very generic definition. But you could also define pi to be the area underneath this function on the entire number line. That's a perfectly well-defined alternative definition for pi. Yeah? Okay. Why is this useful? Why is this useful?
Later you'll see it.
Pardon?
Later you'll see it on.
Well, I want to kind of try and see if I can make it seem useful to you right now, if I can. All right? Because I think these infinite intervals are somewhat strange, but let's see how far I can go with this without going too far off on a tangent. It wasn't supposed to be funny. This is Cal 2. We don't do tangent lines in here. Yeah, in Cal 1, that would be a bad joke.
Still a bad joke.
Still bad? Yeah, you do?
The area or
The whole thing? Yeah. Okay, so I'm going to try and build up to this. This is going to take me a little while, but I think it's worth it, all right? Because there's a lot of other things in here that you may or may not be familiar with. Okay, so I want you to think about an experiment where you have a 6-sided die, all right? And you're going to roll the die. What are the possible outcomes that you could get when you roll the die? You could get 1, 2, 3, 4, 5, 6, right? Those are your 6 outcomes. So I'm going to put 1 here, 2 here, 3 here, 4 here, 5 here, and 6 here. You all following? Okay, now, when I roll this, so these are the outcomes possible, right? These are our possible outcomes. And this right here, I want this to be the probability that we get that outcome. Probability that we get that outcome, all right? So what is the probability that you would roll a 1? 1/6, yes? Okay, so I'm going to come over here and I'm going to graph, like let's say that's 1/6. Then the probability that I roll a 1 is 1/6. So what I'm going to do is I'm going to draw a rectangle here. Okay? Now what's probability I get a 2? 1/6. Same thing. Same thing. Same thing. Same thing. Look at the areas of each of those rectangles. What's the area of each of those rectangles? How wide is each one? 1. So what's the area of this? 1/6, 1/6, 1/6, right? All of them are 1/6, 1/6, 1/6. What's the sum of the areas? 1, right? And that's the sum of the probabilities, isn't it? I mean, if there are only 6 outcomes, then if I add up the probabilities of each one, the probability of 1 happening plus the probability of 2 happening plus the probability of 3 happening plus the probability 4 happening plus the probability of 5 happening plus the probability of 6 happening, that should always equal what? 1, no matter what we're talking about. If it's rolling die or any other experiment, the sum of all probabilities has to be 1 because, well, is that obvious or is that not obvious? You have an experiment that only has so many outcomes. The sum of each probability, let me do it, let me try it this way. How many of you own iPhones? How many of you don't own iPhones? Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say, I don't even know how many people there are in here, but let's say there's 30 people in here, all right? 8 of us have, other than iPhones, the other ones have iPhones, right? Okay, so if I randomly pick a person, what's the probability that they have an iPhone? Yeah, 22 out of 30, right? So if I do it the same way, there's 2 outcomes. The first outcome and the second outcome. Let's say the first one is that you have an iPhone. The second outcome is that not, okay? So if you have an iPhone, we said the probability would be what, 22 out of 30? Right? So if this right here is 22 out of 30, the area of that's 22 out of 30. And then this area right here would be 8, right? 8 out of 30. And so the probability of both of those added up together should be 1. And that's for every experiment, every probability out there. The sum of all probabilities possible has to be 1, because that makes sure that every event can happen, right? Okay. Now, with rolling the die, there are only 6 outcomes, right? You can't roll the die and get a 1/2, right? When I pick a person in the class, they either have an iPhone or don't have an iPhone. This idea of having these fixed numbers, 1, 2, 3, 4, or here, iPhone or not iPhone, These are called discrete random variables, meaning that they can only take on certain values, usually integer values, all right? Integer values. We're not interested in this right now. Okay, this is in probability and statistics. You do talk about discrete random variables, but let's consider a different variable. How about that soda can or whatever is in there, right? What does that say on that label is how much is in there?
8 fluid ounces?
8, really? That's 8 fluid ounces?
Yeah.
You're getting ripped off. Oh, 16 ounces, okay. I was gonna say, man, if they're putting 8 ounces out, you're really getting ripped off. It's like half that can's empty. Okay, it's like $8 for 8 ounces. Okay, so let's consider that, right? Let's say we have a big pallet of those things, right? And we start opening them up and measuring how much is in there. Is it going to be exactly, like let's say we have a super precise measuring instrument. Are they going to all be exactly 16.00000? No. I mean, no, right? They're all, you're going to have 15.9. It's going to be around 16, but they're going to vary a little bit. It's because it's impossible to get exactly 16, right? So if we look at that, then let's say this is 16, and we look at the probability, right? Then what's the probability that it's exactly 16? I mean, it could happen maybe, right? But if this is 100%, let's say 1 is 100%, the probability at 16 is high, but it's not 100, right? What's the probability that it's 17 or 15? Lower, right? Definitely, probably 17 is very, very unlikely, right? Maybe 15 is actually more likely, but the whole idea here is this. As we move away from this, it's going to drop down, isn't it? The probability, and then eventually it's going to get to 0 here, right? Because the probability of having negative amount in there is 0. Yes? Okay. But what about over here? What about over here? It's going to drop down, but it's going to asymptotically approach 0. Now, the reason why, now we all realize that there's no way there's 1,000 ounces in that cup, right? But you can't say 0 yet. I mean, the probability that there's 1,000 ounces in there is like so infinitesimally small, it would be like equivalent to winning the lottery every day of your life for the rest of your life and being struck by lightning every day and surviving for the rest of your life. You know, like we're talking about probabilities that are so infinitesimally small, they're practically 0, right? Yes? Okay, what we need though, is that the total area under this curve has to be what? Has to be 1. Right? It has to be 1 because this is like all the probabilities put together. So go back to the example I just showed you right now. This one right here. Nope. X squared, right? That graph looked like this. Right? And the total area under that was what? Pi, right? So watch, let me change my function. Now, what's the area under that function? 1, right? Because I've scaled it by pi. So now that function's still going to kind of look the same, but now the total area under it is 1. So that function right there is a perfect example of what we call a probability density function, because it's a function that has a total area underneath it of 1, and so it is perfectly suited for these sorts of models where you have probabilities where you need to go out in one direction or both directions forever. Does that make sense or not? This is used in statistics. You've seen the standard normal bell curve? You've seen the bell curve before? The bell curve goes out in both directions forever. And that curve is a probability density function. If you integrate it over the entire number line, you get 1. All right? So the idea that we would ever want to do an integral out in one direction forever and the other direction forever or in both directions forever is absolutely essential to our entire system of probability and statistics for continuous random variables like this. You take something, you weigh it, right? that weight is not going to be dead on exactly to the ounce. It's going to vary, and because of that, we need to be able to find areas under curves.